Hello everyone, welcome back to my channel. In this video, let us discuss about analog multipliers and Wein bridge oscillator. So coming to the first topic, analog multipliers. So this analog multiplier is a device having two input ports and one output port. So the signal at the output is the product of the two input signals. So if the both input and output signals are voltages, then the transfer characteristics is the product of the two voltages divided by a scaling factor K. Okay, so as you can see here we have the dimension of voltage in the figure. Next, from this table, from this table, as we see from the mathematical point of view, so this multiplication is a four quadrant operation. So that is to say that both inputs may be, that means either positive or negative, as may be the output. Okay, some of the circuits use it to produce electronic multipliers. So, however, there are limited to a signal of one polarity. Okay, so if both signals must be unipolar, so we have a single quadrant multiplier, and the output will also be unipolar. So if one of the signal is unipolar, but the other may have either polarity, the multiplier is a two quadrant multiplier. So, and the output may have the either polarity and is a bipolar. Okay. So the circuitry used to produce one and two quadrant multipliers may be simpler than that required for the four quadrant multipliers. And since there are many applications where full for four quadrant multiplication is not required. So it is common to find accurate devices which work only in one or two quadrants. Okay. So now let us discuss about the topic called four quadrant. So here the four quadrant multiplier is a special case of amplitude modulation. So it is also referred to as a ring or a balancer modulation also. So one single change the level of multipliers, that means the level of a second signal. So if the first signal currently has a level of 50%, and the second signal also has a level of 50%, then the output is 25%. Okay. So if the first signal has a level of minus 100%, and the second signal has the level of plus 30%, then the output is a minus 30%. As a four quadrant multiplier harness both positive and negative signals also. So here a typical use is two VCOs running at the audio res fed into the ring modulator. That means a four quadrant multiplier. So the output is a complex set of component tones that don't follow a typical musical spacing biased on octaves above the fundamental. That means the harmonic usually follows the modulation frequency is both added to and subtract from the carrier frequencies. Okay, so the result of this quadrant replace the original carrier and the modulator. Okay, so we have the carrier as a sine wave. That means the fundamental signal at 600 Hz and the modulator was a sine wave at 100 Hz. So the result would be a tone that had a frequency components. Okay, so this is about the four quadrant multiplier. So next we have the topic called IC 1496. So this 1496 is also called as a balanced modulator or a demodulator also. So these devices, that means these ICs were designed for use where the output voltage is a product of an input voltage signal and a switching function, that means a carrier. So typical applications included suppressed carrier and amplitude modulation and synchronous detection, as well as FM detection and phase detection and chopper applications also. So uh, this uh, this semiconductor application, that means this IC, we have some features. So this 1496 IC is an excellent carrier suppression. Okay, and it also have an adjustable gain and signal handling also. So this 1496 has a balanced input and outputs, and it has a high common mode rejection ratio. And this IC device contains 8 active transistors. Okay, so here we have the pin description for the 1496. This is the pin description for the IC 1496. So the coming up to the next topic, we have a sample and whole circuit. So here, a sample and hold circuit is this, sometimes we call it as an SNH circuit also. It is usually used with an analog to digital converter to sample the input analog signal and hold the sampled signal. Okay, so in this circuit, the analog signal is sampled for the short interval of time, usually in the middle range of uh, 10 microseconds, so 10 nanoseconds to the 1 nanoseconds. So after this, the sample value is hold until the arrival of the next input signal to be sampled. So the duration for holding the sample will be usually between few milliseconds to few seconds. Okay, so as you can see here, we have shown a simple block diagram of a typical sample and hold circuit. So this is the block diagram. So here we have the input signal for the simple and hold signal, and we have a sample value will be the output. Okay, so uh, for this sample and hold circuit, if the input analog, if the input analog voltage of an A to D converter changes more than the given that means a given value, then there is a chance that the output digital value is an error. Okay, so for this A to D converter to produce an accurate result, the input analog voltage should be held a constant for the duration of the conversion. So as this name suggests, this S and H circuit samples the input analog signal based on the sampling command and holds the output value at its output until the next sampling command is arrived. So here we have some images. As I mentioned here, these are some of the images for the amplitude, how the amplitude signal through the time for the analog input and the sampled input and the analog hold input. So these are the variations for the sample and hold circuit. So these for understanding the operating principle for this SNH circuit with the help of some simple diagram also. So this sampled circuit, this SNH circuit consists of two basic components. Those are analog switch and as well as a holding capacitor. So the image, the image shows the basic of SNH circuit. So this is the basic SNH circuit of the this is the image for the basic SNH circuit. So here the circuit tracks the input analog signal until the sample command is changed to hold command. So after the hold command, the capacitor holds the analog voltage during the analog to digital conversion. Okay. So now let us discuss about this analog switch. So this analog switch, that means any FET like JFET or MOSFET can be used as an analog switch. So uh, so in this, let us discuss about the JFET. That means the gate source voltage VGS is responsible for the switching of this JFET. Okay, so so here when VGS is equal to 0 volts, that means the JFET acts as a closed switch as it is operates in its ohmic region. So when this VGS is a large negative voltage, that means more negative than VGS, that means it is an off condition. So the JFET acts as an open switch as it is a cutoff. So here the switch can be either a shunt switch or a series switch depending on its position with respect to the input and output. So here we have the images for the for both the shunt switch and also and as well as a series switch I mentioned here. Okay. Let us. These are the two diagrams for the shunt switch as well as in a series switch. Coming next, we have the applications for both S and H circuit. Some of the most important applications are it is used in analog to digital converters, and also used in digital interface circuits also, and as well as in operational amplifiers, used in analog demultiplexers, as well as in data distribution systems, and it is used in storage of output of multiplexers and also in pulse modulation system. So these are some of the applications for SNH circuit. So coming to our next topic, we have this Wien bridge oscillator. So basically, what is this Wien bridge oscillator? So this Wien bridge oscillator is an electronic oscillator, uh, uh, and produces sine waves. Okay, so it is a two-stage RC circuit amplifier two-stage RC amplifier circuit, and it has high quality of resonant frequency, low distortion, and also in the tuning. So it is, considering the very simple sine wave oscillator used by this RC circuit, uh, placed in an LC circuit. So construct the output sinusoidal waveform is called as a Wien bridge oscillator. So the Wien bridge oscillator is also called, this Wien bridge oscillator is also called as a Wheatstone bridge circuit also. It has another name called Wheatstone bridge circuit. So this Wien bridge oscillator is used to find unknown values of a components. Okay, in most of the cases, this oscillator is used in the audio. So the oscillators are designed simply, size is compressed, and it is stable in frequency output. So the maximum output frequency of this Wien bridge oscillator is 1 megahertz, and this frequency is from the phase shift oscillator. So the total phase shift of the oscillator is from 360 degrees or 0 degrees. So it is a two-stage amplifier with RC bridge circuit. So, and the circuit has a lead lag networks. So the lags at the phase shift are increasing the frequency, and leads are decreasing the frequency. So in additional, by adding the Wien bridge oscillator at the particular frequency, so it becomes sensitive. So at this frequency, the Wien bridge is balanced the phase shift of zero degrees. So here the following diagram is this is the Wien bridge oscillator circuit. So in this diagram, we seen as R1 is in series with C1, R3 and R4, and R2 is parallel with C2 to form four arms. Okay, so this in this diagram we can see the two transistors are used for the phase shift of 360 degrees, and also for the positive feedback. Okay, so the negative feedback is connected to the circuit of the output with the range of frequencies. So this has been taken through the resistor R4 to form the temperature sensitive lamp, and the resistor is directly proportional to the increasing current. So if the output of the amplitude is increased, then the more current is offered, more negative feedback. Okay, so coming to this operation, this Wien bridge operation, which means the circuit is in oscillation mode, and the base current of the first transistor is changed randomly because it is due to the difference in the voltage of DC supply. So here the base current is applied to the collector terminal of the first transistor, and the phase shift is about 180 degrees. So then the output of the first transistor is given to the base terminal of the second transistor Q2 with the help of the capacitor C4. So further this process is amplified, and the second transistor of the collector terminal, the phase reverse signal is collected. So here this is in this the output signal is connected to the phase with the help of the first transistor to the base terminal. Here the input point of the bridge circuit is from the point A to the point C. Here from the A to the C. So the feedback of the circuit is the output signal at the second transistor. So here the feedback signal is given to the resistor R4, which gives the negative feedback. So in the same way, the feedback signal is given to the base bias resistor R4 and it produces the positive feedback signal. Okay, so here we have two capacitors C1 and C2. So by using these two capacitors C1 and C2 in this oscillator, it can behave continuously, continuous frequency variation. Okay, so these capacitors are the air gang capacitors, and we can also change the values of the frequency range of the oscillator also. So here and we also so here this is a Wein bridge oscillator using 741 IC. So this oscillator is a low frequency oscillator. That means the Wein bridge oscillator operational amplifier is used as the circuit, oscillator circuit, and it is working like a non-inverting amplifier. So remember this works as a non-inverting amplifier. Okay, so hence the feedback network. That means the feedback network is not given to any phase shift. So the circuit is observed like an Wein bridge on RC series network of one arm and the parallel RC network for the another arm. So here the resistors RI and RF are connected to the left two arms. Okay, so this is the circuit diagram for the Wein bridge oscillator by using 741 IC. So coming to the next topic. So coming to the next topic, we have the applications. So this Wein bridge oscillator is used to measure in audio frequencies, as well as this Wein bridge oscillator used to design the long range frequencies, and it also produces a sine wave. So these are the applications, some of the applications for this Wein bridge oscillator. And coming to the advantages and disadvantages for this Wein bridge oscillator. So for advantages, it is distortion testing of power amplifier. It is used in it helps to distort testing of power amplifier, and it also supplies the signals for testing filters also. And it is for this Wein bridge oscillator is best for the excitation of AC bridge, and by a long distance can be spanned by the resting beams also. So these are the advantages, and coming to the disadvantages, this Wein bridge oscillator is not used for the high resistance. So here the circuit needs the high number of the other components. So here the limited output frequency is obtained because the amplitude and the phase shift characters of the amplifier. Okay, so this is for the today's topic. So I hope you understand this topic. Thank you.